All right, welcome to our presentation on reactions in aqueous solutions. This is part one of two. In this part, we're going to talk about what it means to dissolve and form ions, talk about your net ionic equations, as well as some acid-base chemistry. So a solution is defined as a homogeneous or homogeneous mixture of two or more pure substances on which the solvent is present in the greatest abundance. So the solvent is the stuff that's doing the dissolving, and everything else is the solute, the stuff that is getting dissolved within the solvent. We call dissolving dissociation. When an ionic substance dissolves in water, the solvent pulls the individual ion apart. This is called solvation, or it solvates them, and again called dissociation. So in this case, we've got our sodium chloride and our chlorine, our chloride ion, is being solvated by the water. They're surrounding it and attaching it, and so is the sodium plus ion, so it's dissolving the stuff. And this is creating an electrolyte, the substance that is dissolved into ions when dissolved in the water. So the chloride ion is an electrolyte, so is the sodium ion. And then a non-electrolyte can dissolve in water, but it does not totally dissociate into ions. So in this case, they're showing methanol being dissolved in water. The methanol totally becomes uniformly distributed in the water, but notice the water molecule is not breaking apart the methanol molecule. So how do you differentiate between electrolytes and non-electrolytes? Basically, if you think of things as ionic or molecular and think in those terms, you'll be all set. So soluble ionic compounds tend to be electrolytes. So if you see a metal bonded with a non-metal, you're good to go. Right? These things are all going to be strong electrolytes. They're not ever going to be weak electrolytes. Versus something that is a molecular compound, an ionic compound, strong acids completely dissociate, so those are strong electrolytes. Weak acids and weak bases sort of dissociate a little bit, so they're weak electrolytes. Everything else doesn't do anything. So like sugar would not be an electrolyte at all. So again, molecular compounds, they contain a covalent bond, tend to be non-electrolytes except for the acids or bases. So the strong electrolyte, like I just said, completely dissociates into its ions. A weak electrolyte only partially dissociates, and then if it's a non-electrolyte, it doesn't dissociate at all. So if you have pure water, no water conducting because there's no ions, there's no electrolytes to conduct that electrical charge. We can put in sucrose, which is just sugar, and that doesn't conduct electricity. And then salt obviously is going to dissociate into sodium ions and chlorine ions, and it does conduct the electricity. Strong electrolytes, like I just said, are strong acids and strong bases. This is something you just need to memorize, commit it to memory. The strong acids, there's only 7 of them. You need to know them. And then strong bases are group 1A metal hydroxide, so lithium hydroxide, sodium hydroxide, and so on. And the heavier parts of group 2, so calcium, strontium, barium. We're leaving out beryllium and magnesium. They're not heavy enough. And then soluble ionic salts, like I just said, things that ionic compounds that are soluble are going to be strong electrolytes. A precipitation reaction is when you mix ions and then they form something that is insoluble. They form a precipitate. So in this case, you're getting this yellow precipitate when these two solutions are mixing. And we can predict what's going to be soluble by the solubility guidelines, but the AP board, they don't really focus on the memorizing of those anymore. So you don't have to worry about that as much. They usually tell you if something is soluble or not soluble, or you'll just have to look at the equation and see, oh, hey, look, now one of my products is a solid, so something in there is insoluble. What you do need to know, though, is that group 1, alkali metals are always soluble, nitrates are always soluble, and ammonium is always soluble. So those you do need to know. But there's a whole bunch of other solubility rules that we don't need to know anymore. They'll pretty much give you the information that you need. Metathesis, or an exchange reaction, comes from the Greek word, it means to transpose. You're probably familiar with this kind of reaction. We might know it as a double replacement reaction. And so in this case, you look down here, you have your silver nitrate and your potassium chloride, and then everything just swaps. The silver combines with the chlorine, and then the potassium combines with the nitrate. And so everything just swaps. So they transpose ions. One thing is you have to pay attention to what is present, solid, liquid, gas, aqueous, and that sort of thing, just so that you just get in the habit of that. It's easy just to leave those things out and think they don't matter, but they do, because when you look down here and you notice, oh, hey, look, now my silver chloride is a solid, so something special was happening there. And those are the sorts of things you need to be aware of. So definitely get in the habit of always writing its form, solid, liquid, gas, or aqueous solution, the species. Some different types of equations. The molecular equation is what you're most familiar with. Lists the reactants and products in their molecular form. So again, we're still looking at the silver nitrate and potassium chloride, and then silver chloride and potassium nitrate. That's the molecular equation. The ionic equation, all the strong electrolytes, the strong acids, strong bases, are dissociated in their ions to more accurately show what it really looks like. Because if you have these things in an aqueous solution, you don't have silver nitrate anymore. Those guys have become dissociated. Now you have silver ion, and you have nitrate ion, and you have potassium ion, you have chlorine ion, all swimming around in that aqueous solution. And then you produce this solid silver chloride, and there's still some potassium hanging out, and there's still some nitrate hanging out in that solution. Basically, when you're writing the net ionic equation, though, again, because it's a net ionic equation, we don't really care about the stuff that doesn't change from the reactants to the product, so it's not really involved in the reaction that we care about. So in this case, nitrate is here, nitrate is there. Obviously, it didn't change at all. We sort of like cancel it out. Same thing with the potassium. So the things that didn't change, we call those the spectator ions. They're just sort of watching the reaction happening, watching it unfold. And so once we do that, the only things that are left is the net ionic equation. So that's what we actually care about. The silver ion, the chlorine ion react to produce the silver chloride. So just to summarize, when you're writing an ionic equation, you're going to start out with the balanced molecular equation. Then you're going to dissociate all the strong electrolytes. Here's where you got to be careful. If you have something that's a molecular compound that's not going to be a strong electrolyte, you leave it together, right? Because it's not going to break up into its electrolytes. It'd rather stay together. So only the strong electrolytes. Cross out anything that remains unchanged, and then write the net ionic equation with the species that remain. This is something you're going to want to practice with and make sure you're pretty good at, because this kind of keeps one of those things that keeps cropping up and over again. And if a student just sort of like barely fudges his way through this unit, they kind of find themselves kicking themselves later on down the line, because this is something you need to know a lot of. Moving on, I'm going to talk a little bit about acids. Acids and bases, two common reactions or two common things that are aqueous solutions. A couple different definitions of acids. Sort of the traditional definition is the Arrhenius definition, in which an acid is anything that increases the concentration of H+. We also have what's called the Bronsted-Lowry definition of an acid, and that's anything that donates protons. Right? Usually it's going to be H+, but it doesn't have to be. And then conversely, there are only 7 strong acids, like I said: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, perchloric. You need to know them. You need to be able to recognize when you see them that they are strong acids. And you need to know that because you need to recognize, oh yeah, hey, those are strong acids. They're also strong electrolytes, so they're going to be dissociating completely. Versus if it's something that's not a strong acid, it's not going to be dissociating completely. Like acetic acid, for example, is not going to dissociate completely. Bases, again, the definition you're probably more familiar with is something that increases the concentration of OH-. The Bronsted-Lowry definition is just that anything that accepts a proton. And the strong bases, like I already said, the alkali metals, so group 1 with a hydroxide ion, and then the heavier group 2, calcium, strontium, barium. Acid-base reactions, basically the acid donates a proton to the base. Pretty simple. Right? So in this case, water can act as an acid. It's donating a proton over here to the ammonia, creating ammonium, and then you've got your OH-. Neutralization reactions, generally what happens when you mix acids and bases together. You get a salt in a water, something you've probably heard before. So in this case, we've got acetic acid plus sodium hydroxide, and you're getting a salt. So sodium acetate and water. In this case, a salt doesn't necessarily need to be sodium chloride, which is what we often think of when we think of salt, but a salt in this case is an ionic compound whose cation comes from a base and the anion comes from an acid. So it's basically the byproducts of a neutralization reaction. All right, neutralization reaction. Strong acid reacts with a strong base. You get this net ionic equation. Well, actually, this is the molecular ionic equation right here. HCl plus NaOH yields table salt, NaCl plus H2O. We take out those spectator ions, right? The chlorine ion, sodium ion. And what's left over is the H plus reacts with the OH minus to yield water. So that's our neutralization reaction. It's the acids and bases have neutralized each other. Sometimes the reactions give you products that are a little bit unexpected. So in this reaction with calcium carbonate and hydrochloric acid, you'd expect to get carbonic acid, but instead this carbonic acid decomposes to give off carbon dioxide instead. And so when these guys, carbonate or bicarbonate, react with an acid, you still produce a salt, but you're going to produce carbon dioxide and water. So those are just reactions that you have to remember when you've got this going on. This is when you're going to get carbon dioxide. So this is kind of like fizzy water or seltzer water, or you do baking soda plus acid. You've probably seen those, the volcanoes. That's what's going on. You're producing that carbon dioxide. Similarly, sulfites react with acid to produce a salt, sulfur dioxide, and water. That one is a little bit more expected, but just keep in mind that that's going to be not so fun of a product. Let's just put it that way.